Hi all and Assalamualaikum. Today we are going to continue with our discussion on Chapter 3, Current Flow in Homogeneous Semiconductor, focusing on optical processes in semiconductor. For revision, we have discussed in generation and recombination process in semiconductor previously, in which generation is a process of electrons going to conduction band from the valence band, producing electron and hole pair. And recombination is a process of electrons in conduction band relaxing to the valence band, annihilating an electron and hole pair. At equilibrium, the generation and recombination rate is equal, thus the carrier concentration are constant, N node and P node. Generation process in a semiconductor can happen in the presence of light, and also recombination process in a semiconductor can produce light. We call this optical processes in semiconductor. At the end of this video, I hope you will be able to understand and explain the optical process in semiconductor. We understand that generation process can happen when there is enough energy for the electrons at the valence band to jump to the conduction band. The energy can be in the form of thermal energy or optical energy. Light produces photon energy or optical energy. When the light is shined on a semiconductor, if the photon energy is larger than the band gap of the semiconductor, the electron will have enough energy to jump from valence band to conduction band, which means the generation process can happen and results in the creation of electron and hole pair. The electrons and holes generated due to the photon are called excess carriers. When there is light, optical absorption will happen. Optical absorption is a process where electrons absorb the energy from light or photon energy. From the figure, if one particular electron at room temperature has the energy of E node and on top of that absorb the photon energy, thus the total energy for that electron, E1, is E node plus H nu. When optical absorption happens, photon is annihilated to obey the energy conservation law, where photon energy is converted. And if the total energy E1 is larger than the band gap, the electron will be able to jump to the conduction band because the energy consumed by the electron E1 is larger than the conduction band level, EC. Thus, in order for an optical absorption to happen, photon energy H nu must be larger than Eg. Besides the energy conservation law, wave vector k also must be conserved. Usually, since the photon's wave vector is very small, the optical transition is vertical, as shown in this figure. For a direct gap material, the transition of electron from valence band to the conduction band is simple. A direct gap material is a material having the lowest energy point of the conduction band at the same k point of the highest energy point of its valence band. Thus, the transition of electron happens directly. As for the material having lowest energy point of conduction band not at the same k point of the highest energy point of its valence band, it is known as the indirect gap material. The transition of electron from valence band to the conduction band requires the energy to jump and also the energy to move k. Thus, photon is needed to provide the energy, and also phonon is needed to move the lattice, which is needed to change the k. To conclude on absorption, photon energy must be larger than the band gap for absorption to happen. Direct gap materials are efficient materials that can absorb and emit light. Their examples are gallium arsenide, indium phosphate, and zinc oxide. However, on the other hand, indirect gap materials are not as efficient as the direct gap materials because they need both photons and phonons for generation and recombination process. The examples are silicon, germanium, and gallium phosphate. However, majority of our devices are made of silicon. Although they are not efficient, but they are abundant. Thus, cost-wise, it is still the best choice of material. Next, we will discuss on emission. Emission is an inverse process of absorption. It is a recombination process of which electron relax from conduction band to valence band. Under energy conservation law, when the electron relax from conduction band to valence band, the electron will release energy. The energy can be released in the form of photon or light, phonon, which will be converted to thermal or both. In emission, the recombination process will produce light. Same with absorption. Direct gap materials have simpler emission process in which electrons from conduction band relax directly to the valence band and emit photon, and in some cases photon and phonon. However, for indirect gap materials, the electrons will never relax diagonally due to the K conservation law. Electrons may relax directly to conserve K, but this is unlikely to happen. The key points for emission. Emission happens when electron at conduction band, which is at higher energy level, returns to the empty states in valence band, which is at the lower energy level. The electrons will release energy during the transition from higher energy to low energy states in the form of photon, which is called emission, while K is conserved. Direct gap materials are efficient emitters, which is suitable for the devices such as LED and laser materials, and indirect gap materials are poor emitters. So we have known that under light, absorption of photon will result in generation of electron and hole pair. This will create excess electrons and holes denoted as delta N and delta P. So now the total concentrations of electrons and holes under the elimination are given as below. N is equal to N naught plus delta N, and P is equal to P naught plus delta P, and remember that delta N is always equal to delta P. If all of the material is under the light, then the excess carrier is uniformly generated. However, if the light is only shined at one point, for example, as shown in this figure, the excess carriers are only generated at that particular point. The carrier concentration at that point will become N equal to N naught plus delta N and P equal to P naught plus delta P. This will induce variation of carrier concentration and further induce diffusion current. At the dark end, or if the light is turned off, the excess carriers will recombine and the material will return to the equilibrium state, of which the carrier concentrations do not involve delta N and delta P. Here, N is equal to N naught and P is equal to P naught. Thus, for conductivity calculations, since the carrier concentration under elimination includes delta N and delta P, the general equation for conductivity is given in the top equation, and this will become the lower equation. This is the total conductivity of the sample. You can also calculate the conductivity induced by light using the sigma PC equation, whereas the conductivity of the sample without light is given as the sigma naught equation. For the summary, light can induce generation process when photon is absorbed. This will produce excess carriers delta N and delta P. Delta N is always equal to delta P. When electrons return to valence band from conduction band, emission happens in form of photon or phonon emission or both. When light is turned off, excess carriers will recombine and the sample returns to equilibrium state. So that's all for now. Please do not hesitate to ask questions and discuss on this topic via WhatsApp or at the comment section in our FB group. Thank you.